Section 3.7 also contains information about the derivatives of inverse trig functions and the derivative of inverse functions. We'll start with inverse trig functions. An inverse trig function is like y equals inverse sine of x. This can also be written as sine y equals x. So what I'm going to do is use that form, sine of y equals x. And I'm going to take the derivative of both sides. The derivative will be taken with respect to x. So on the left, we get the derivative of sine as cosine, but the variable here is y. So we're taking the derivative implicitly, and that means I have to consider y as a function of x. So I'm going to multiply by dy dx. On the right side, I'm taking the derivative of x, which is 1. Getting dy dx by itself, I get 1 over cosine y. So this is the derivative of the inverse sine, but it has the variable y. So I need to address that. We know that y is between negative pi over 2 and pi over 2. And we're taking the cosine here of y. So the cosine of y is going to be greater than or equal to 0 in those quadrants. We know it's positive, and I'm going to bring in a little fact you should remember, and that is sine squared plus cosine squared equals 1. I'm going to manipulate that equation to try and use it. So here I'm getting the expression cosine y, and I know it's going to be positive. I already established that. So cosine y equals the square root of 1 minus sine squared y. I want to replace this cosine y down here because it has the y variable, but I still have the y variable in this equation over here that I've been working with. So I'm going to go back to my original setup. Look back at the top right here. I had sine y equals x. Well, I have a sine y down here. I can replace that with x, and I'll have to square it. So now I can write cosine y equals the square root of 1 minus x squared. There we go. Now I can put this in place of cosine y in our derivative formula. So instead of cosine y in the denominator, I'm going to write the square root of 1 minus x squared. I'll write that in the summary. The derivative of the inverse of sine is 1 over the square root of 1 minus x squared. Now we could do that again to find the derivative of cosine inverse, but I'm not going to do that on this video. So I need to tell you that the derivative of cosine inverse is very similar. You could find it in the similar fashion, and it is simply negative 1 over the square root of 1 minus x squared. So we're going to practice with those two for a moment. My first example is x times inverse sine. So if I want to find the derivative of y, meaning I want to find dy dx, I'm going to have to do a product rule. So I'll have the first times the derivative of the second. We just learned the derivative of inverse sine is 1 over the square root of 1 minus x squared plus the second times the derivative of the first. So here's the second function, and the derivative of the first is 1. So we are done. In the second example, we're going to take the derivative, and we'll use the notation f prime of x, and the coefficient there is 3, so we'll keep the coefficient. The derivative of arc cosine is negative 1 over the square root of 1 minus x squared. But in this case, the angle is 2x. So it's going to be the quantity 2x squared. And then we're going to do chain rules. So we're going to multiply by the derivative of 2x, which is 2. F prime of x equals negative 6 over the square root of 1 minus 4x squared. You will also need to know the derivative of inverse tangent. That will be very important. I have included the derivative of the reciprocal functions inverse. They're there for your reference, but it is the derivative of inverse sine, inverse cosine, and inverse tangent that we will cover in AP Calculus. And now for the derivatives of any inverse function. I have a graph here where function f is the top curve and f inverse is the lower curve. And I have drawn the line y equals x. The function and its derivative are always reflections of each other in the line y equals x. So you can see it's drawn that way here. I'm going to locate a point on f, any point at all. So I'm going to call it x comma y. Point on f called xy, then there has to be a point on the inverse of f called yx. So we're going to use that concept in a moment. Now, I want to take the derivative of f inverse. I'm going to use this form of the equation to do that. So let's take the derivative with respect to x on the left and take the derivative with respect to x on the right. The derivative of f of y, of course, is f prime of y, but y is a function of x, so I have to do chain rule. So I'm going to multiply by the derivative of y with respect to x. And the derivative of x is 1. We have the first derivative is 1 over f prime of y. But we have the same problem here that we had on the last page. The problem is there's still a y in this definition of derivative. But we don't need to worry because look back up at the top. We said that y equals f inverse. So I'm going to take that and substitute it in for y down here. So dy dx is 1 over f prime of f inverse of x. That is your formula for the derivative of the inverse function. In our first example, we are given f of x, and we have to find the derivative of f inverse at 2. That 2 is obviously an input for the inverse. Well, if you remember the graph above, an input for the inverse is an output for the original function. So I'm going to go over here where the function is, and I'm going to replace f of x with a 2. That's because f of x is the output. So 2 equals e to the 2x plus 1. I'll just continue with this equation and try to solve for x. So first subtract 1 from both sides. We have e to the 2x equals 1. Well, hopefully you noticed that's an exponential on the right side, and the only way an exponential equals 1 is if the exponent were 0. So that's like 1 equals e to the 0. That's how you would get 1. So 2x must be equal to 0, which means x is equal to 0. So now we have on f, the input is 0 when we gave it the output of 2. That means on the inverse, the input of 2 gives us an output of 0. So now with that information, we can go ahead and find the derivative of the inverse. Here's the inverse. We're going to take the derivative of it at 2. Let's bring the formula in. The formula in the box up above. 1 over f prime of f inverse at 2. Well, we now know that f inverse of 2 is going to give us 0. So this is equal to 1 over f prime of 0. Well, we don't have f prime right now, but we can get it. Take f and find the derivative. The derivative of f is 2e to the 2x. And then you can use it to find f prime of 0, which is 2 times e to the power 2 times 0, or 2 times e to the 0 power. And we already covered the fact that e to the 0 power would be 1. So we're getting 2 as the value. So that means this answer is 1 over 2. Okay, last example. We're going to do this again. We're being asked for the derivative of the inverse at 10. So this 10 is the input for the inverse. That means it's the output for f. So go over to f and put 10 in place of the output. Now I know when you see the cubic here, you may want to use your graphing calculator. But in the book, they did not designate these as technology questions. And that is because they want you to pause for a moment and analyze the equation, because you could come up with a value for x quite easily that would give you this 10. So what number cubed plus that number would give you 10? That cannot be a very big number. So if you start with 1, obviously 1 cubed plus 1 is 2, then try the next bigger number, so try 2. 2 cubed is 8, plus 2 is 10. So they are thinking that you could look at the equation and glean the value of x from that. So what that means for us is that on f, we have an input of 2 giving us an output of 10. So the inverse of f would have the ordered pair switched. So the input of 10 would give an output of 2. Let's go back now and set up the derivative of the inverse. So here's the inverse. I'll take the derivative at 10. Bring in the definition of derivative. 1 over f prime of f inverse at 10. So we know now that f inverse of 10 is 2 from the ordered pair right above. Next, I will find the derivative of f. So let's take the derivative of f. F prime equals 3x squared plus 1, and evaluate that for 2. So 3 times 2 squared plus 1 is 3 times 4 plus 1, which is 13. So this is 1 over 13.